1, 2, 3. 1, 2, 3. A este se le bajó, parece. 1, 2, 3. Pero estamos... Ahí me están avisando el retorno primero. Que este es de acá, pero este es del computador. No tiene nada. 1, 2, 1, 2. Pero estoy pegado aquí. Ahí, 1, 2, 1, 2. Ya. ¿Y este? ¿El audio? ¿Cómo se escucha este? 1, 2, 1, 2, 1, 2, 1, 2, 2, 3, 4, 1, 2, 3, 4. Vale. No, que estamos probando este otro. 1, 2, 3, 4. ¿Sí? Bien. 1, 2, 1, 2, 1, 2, 1, 2, 3, 4, 1, 2. Ahí creo que sí está bien. Sí.
Disculpa, voy a subirle el volumen.
1, 2, 1, 2, 3, 4.
Acércate más al micrófono.
1, 2.
Para que te inclines tú menos.
1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4.
El trámite de lo que tenés que decir. Y si no te acordáis, di que no lo he visto.
Ya. 1, 2, 3, 4. Sí, ahí. No, hay mucho. 1, 2, 3, 4. 1, 2, 3, 4. Sí, ahí sí. 1, 2. 1, 2, 3, 4. 1, 2. Sí, creo que sí. 1, 2, 3, 4. Ya son las 10, ya deberían llegar en cualquier momento.
Sí, no te he mandado correo nunca.
De hecho, estaba tomando café.
Ah, ya.
Felipe Guzmán, Felipe.
Porque reconocí a tu profesor.
¿Tu correo era Felipe Guzmán?
Un Felipe Guzmán Music.
El Liope, pues.
Qué bonito el corte de la camisa.
O no, mira, tiene el bolsillo al revés.
¿Y es igual el bolsillo?
No, este es como una capita. ¿Sí? Este igual.
Música.
Sí.
Todo junto.
Felipe Guzmán Music. Sí, eso. @hotmail.com.
Te he mandado correo, no me aparece.
estamos acá para el examen de grado de doctorado en Ingeniería Eléctrica de Felipe. Voy a explicar un poco antes de comenzar la parte protocolar, que debo leer acá el acta, ¿ya? El procedimiento. Primero Felipe va a hacer su presentación, el comité va a hacer preguntas a Felipe para evaluar su profundidad de los conocimientos y luego de eso le vamos a pedir a toda la audiencia de que se retire de la sala para que el comité pueda deliberar. ¿Ya? Voy a agradecer que todos los presentes puedan manifestar su apoyo a Felipe hasta que yo vea el acta final, ¿ya? No en forma intermedia, ¿ya? Para poder mantener el nivel de ceremonia del evento. ¿Ya? Voy a partir leyendo el acta entonces y luego Felipe va a hacer la presentación. El alumno Felipe Orlando Guzmán Vega, RUT 18.183.890-6, ha solicitado al director del doctorado de la Escuela de Ingeniería Eléctrica, que es quien le habla, se le autoriza a rendir su examen de grado para obtener su grado de doctor en Ingeniería Eléctrica, cumpliendo con todos los requisitos mencionados en el reglamento académico. Estos son: aprobó todas las asignaturas del programa, obteniendo un promedio ponderado de 6,5. Desarrolló su estadía de investigación en la Universidad de Arizona, Estados Unidos, desde el día 2 de enero de 2023 hasta el 28 de junio de 2023. Realizó una publicación vinculada a su tesis. Aquí coloco una, pienso que tienes más, pero esta es la que nos enviaste. Compressed video vía IR uses illumination, Journal Optic Express, donde Felipe es el autor principal. Aprobó su tesis de doctorado con el tema called Aperture Strategies for High Speed Video Sensing. La comisión de este examen está integrada por Dr. Ryoichi Horisaki, Associate Professor at University of Tokyo, Japan, Dr. Pablo Mesa, profesor asociado de la Universidad de la Frontera, Chile, Dr. Gabriel Mosilla, profesor adjunto de la Pontificia Universidad Católica de Valparaíso. El director del programa participa como ministro de fe solamente, no va a evaluar a Felipe, y también obviamente se invitó al director del ES, el doctor Esteban Vera, que tampoco va a participar de la evaluación. Felipe, en este momento tienes 40 minutos para presentar.
Thanks, Professor Mauricio. First, I want to welcome the committee and thanks to be here in person. That means a lot to me. And hopefully this presentation will be as fun as I try to make it as possible. And for especially for Professor Horisaki, thanks to travel all over the world to be here. And if you excuse me, I am going to talk a few words in Spanish to welcome my family. Gracias a mis padres y a mi esposa por estar aquí. Eso significa mucho verlos aquí sentados. A mis colegas del Doctorado, muchas gracias también por participar. Y sobre todo a mi profesor guía, que me ha sido mi mentor y ha estado siempre ahí para apoyar. So, my thesis is a compendium of different works, all related with high-speed video. So, first I want to start with this. This fact, in the platform YouTube, each minute you pass, 72 hours of video content is uploaded. So this, I like this fact because this is only related to video, but the massive amount of information that all the people are uploading to the internet are becoming really mind-blowing. So we don't have time, with this metric, we don't have time in the universe to watch all the content, because each time we watch 1 minute, we have 72 hours to keep watching. And all this big data has been really useful in new tools such as artificial intelligence. For example, we can collect all the data available on internet and create some generative models. For example, this one was recently published, when only with this prompt you just give this text and the neural network is capable to generate video content. But all the information can come for this called plenoptic function. The idea of the plenoptic function is that each object has a lot of information that can irradiate through space. And each sensor we design is always going to be a constraint or a trade-off. We cannot measure all. So for example, in video, we measure space, a 2D projection of space, and also we measure time, but we also lose information, or we have limited information about polarization or color, or we lose the 3D properties. So other people develop sensors maybe to measure the 3D properties of an object, but they lose color or they lose time because the time it takes to collect the data. And in the context of images, I like this work. I mean, when we consider Giovanni Battista della Porta work, when they describe the phenomena, the optical phenomena, and also the most iconic one, the pinhole camera, which is the most simplest way to form an image. I like really much this word because they call it magica naturalis. So basically it means natural magic. And that's how I feel when I first started to learn about these novel concepts. But the problem of forming images then was how we can record it. So back then in the camera obscura, they used to paint in the projection. So a painter has to record the process. But now with the development of photography, we managed to develop chemical ways to record and store the image information. And this gives rise to the photography era. And then some intelligent people think about what happens if we get a lot of pictures in different instants of time, and then we pass it one to another in a rapid way. And then it borns the idea of motion picture. And I really like this video because it was the first motion picture ever captured, and it is still preserved up to today. And it's just a simple walking outside in a house of Louis Le Prince. But for cinema, this 24 frames should be enough to fool the eye, to think we have dynamic, we have movement. But in science, 24 frames is not always a good thing. Maybe we need more. And there is a lot of fields that having more frames per second is more useful. For example, in particle analysis or in material analysis, even in sports, or even in astronomy, there are some applications when we have to record the turbulence. And all of this needs a high-speed camera. A high-speed camera is just a traditional camera, but we have to modify the sensor and to consume less power. But even that is not sufficient because if you see, there is a huge apparatus. And the other problem is that when you collect a lot of frames in just 1 second, maybe thousands of frames, we can give a little bit of calculation, and we can see that for a resolution of 2000 by 1000 and 12 bits of bit depth, and now in 9000 frame rates per second, if we record in this property for 1 second, we have 55 gigabytes of data, which can fill most of the hard drives we have today in just a few minutes. And this is a problem. So people start to think about how we can compress the data. And compression, it works in a really simple way. So for example, you can see my face here. And the good thing about natural images, as myself you can see, is correlated. So if I move around, you can see in a portion of the image, the pixel values are really almost the same. So why we need to store all the pixel values if we can infer that we can use this assumption to compress it? And the basic principle of compression, we collect some data, for example, this balloon, and then we have to make a decision. How we can compress it and what sacrifice we are willing to take. If we are not willing to lose any information, then we have to compress in a lossless manner. So as the word it says, lossless doesn't give out any information. However, if you can notice, the compression capabilities are really limited. For example, in this balloon that weighs 2 megabytes, with Huffman coding, we can only get 1 megabyte of compression. But then, if we assume these limitations of the human perception, and we are willing to lose some information, then we can compress with lossy. And lossy compression have a lot of options. If we have still images, we can use JPEG, a really successful algorithm that we use until today. Or if we have video, we can compress using MP4. And here the compression capabilities are really big. So now our 2 megabyte image can be as low as 2 kilobytes. But this is the problem with this one is first we have to collect the data and then compress it, so making inefficient. So a more efficient way should be if we know we are willing to lose some information in the human perception, we can just collect the data we need. And then we call this concept compressed sensing. I really like this example. So this is one concept of compressed sensing called single pixel imaging. The idea is that if you use projections of the scene, here we can see the cameraman, and we can read in only 1 pixel, with less measurements, we can reconstruct the image. So here we are not using the Nyquist theorem of sampling that says we have to sample twice the maximum frequency. With the sparsity assumption of natural signals, we can recover the image with less measurements than the Nyquist require. And when I was studying computational imaging in my postgraduate courses, and studied the concept of single pixel imaging, for me personally was my magica naturalis. It was my magical moment that how this black box can work, how Lasso can reconstruct this image with just a bunch of intensity values with random projections. But then I start to move a concept of time. I always liked video. For me, in my studies, when I was younger, I was planning to be a film director. So I was really into motion picture. So I started to see that this concept of compressed sensing is also applied in high-speed video. And one of the first works that developed this technique was called coded aperture compressive temporal imaging, proposed by Professor Patrick Lull in 230. And the idea is that using the same concept of random openings and closings of the aperture and in the exposure of the camera, we can compress or multiplex multiple frames in the measurement. So as you can see in the example here, we only use the snapshot in the right. We can reconstruct a video. However, as you can see, the results are quite a bit noisy, but developments in deep learning and also signal processing has leading us to results so good as this one. So this one was one of the first 4K videos in color. So if you can see the snapshot, the only capture you take is the one of the top left, and there is different proposals for reconstruction, but you can see the reconstruction is really good. But this one, if you can notice in the optical implementation, it has its problems. So we can, for example, summarize any coded aperture system in temporal. We can summarize as this. We have a moving object, we have a relay lens, then we have to codify the aperture. In the original case of cacti was shifting as a mask, a perforated mask, and also another relay lens to get to the sensor. And on the bottom, you can see my implementation of Cacti, where I use a DMD, which is an electronical control device. It's not shifting, now it's sampling it has a lot of mirrors that you can activate individually in an implementation of other colleagues of the same field. And you can notice that there is a lot of optics involved, becoming this optical implementation a bit bulky. You have to add an extra hardware to control precisely. And also there is a problem with calibration. Not always the mirror size of the coded aperture is going to be the same as the pixel of the sensor. So you have to calibrate to have a good relationship between those two with considering the magnification of the lens systems. And also, if this system starts to vibrate in harsh environments, probably the coded aperture can be easily damaged. Other challenges that this compressed sensing has is scalability. A lot of work has been done to tackle this with more efficient networks or more efficient optimization algorithms. But at the end of the day, you cannot compress forever. For example, here in the right, you can see a reconstruction of 4, 8, 12, and 32 frames. And when you more compress, when you have more frames compressing it, the reconstruction becomes noisier and noisier. Because the algorithms have to disambiguate the information of many pixels in time. And this increase a lot, and the noise increase a lot. Each mistake you have is going to accumulate, leading to worse results. So this is a summary of the two challenges that I want to tackle in this presentation. Challenge 1 is the optical complexity, and challenge 2 is the scalability. We are going to call this CH1 and CH2. That's going to be useful a bit later. And my research goal is going to be tackle these challenges associated with high-dimensional data queues, but in the context of time. And I want to use a compressed sensing as a tool to enhance effectiveness and efficiency in current sensor technology. So warning ahead, we're going to have some equations, but don't worry, it's not too much. First, we want to assume a continuous dynamic object. For example, a balloon that is falling. And we want to quantize the information. That's what we call frames. So now we have collected our data, and these frames are stacked together to form a tensor. We are going to call this tensor X. And this is the information of the object embedded in discrete quantums, where we can call it voxels, for example, if it's volumetric. And the acquisition model is we have a tensor of that represents the object. We have another tensor S that represents our shutter or our colored aperture properties. Notice that they have also an index K, which it means is dynamical. And all of the information is integrated in a sensor, which we call is going to be the matrix Y. And if you notice, when we change and codify, the sensor is going to expose all that information. So then the proposal of all the works we are going to discuss here are basically in how can we design S. And each work is going to be oriented of one specific challenge. So the first three is going to be challenge 1, which, if you recall, is of optical complexity. And then the last one is going to tackle challenge 2, which is scalability. The first work is using a concept of rolling shutter. So rolling shutter is just basically a consequence of sensing design. So in CMOS tradition, each pixel is moving to the buffer and is stored in a place when they can store the information, and then each pixel is read it one at a time. This process is slow and expensive, and also CMOS technology has presence of blooming, which is the leakage of charge between the pixels when there is a lot of. On the other hand, CMOS technology was proven to be really efficient. It has low power, is cheaper, and you can achieve higher resolutions and with fast readout time. But if you notice, there is a parallel multiplexer, so we are reading one route at a time, and this has a distortion, what we call it rolling chatter. And rolling chatter is just basically we are sampling each row at a different time. So in global chatter, for example, each row of the sensor is exposing to the object and read it at the same time. But in rolling chatter, these one are displaced. So the circuit doesn't allow that the readout time, which is black, to be overlapped. And this has consequence when if we have an static image, like for photography, for example, there is no problem with rolling chatter. But if we have a moving image, then the problems start to occur. There are some distortion, what we call wobble, skew, or aliasing. On the top, you can see temporal aliasing. If we have a strobe light, you can, in a rolling chatter, you can see if the frequency of the rolling chatter match the frequency of the light. You can see the LED turn on and off at the same time in the image. If you have fast rotating objects in the middle one, you can see they become deformed, or even in linear motion, just as the car. So this was a huge deal for the computer vision community because algorithms suffer a lot when they are in presence of rolling chatter. But from my point of view, this is an opportunity because we are sampling different instants in time. This can behave as a coded aperture. So if we have our traditional coded aperture with all these extra optical elements to codify randomly, okay, this is proven to be good. But we can do the same with rolling chatter, we are sampling one row at a time. And if we show the tensors how different are, the first thing we can see is that in rolling chatter we don't have a lot of control on when activate each voxel. But what happens if, for example, I increase the exposure? Then the tensor that describes the chatter activate more rows in the given time, allowing some bit of multiplexing, or even we can change the orientation of the camera, and we are changing also the orientation of the sampling matrix. So the proposal I did in this work was using a camera array to increase the sampling density. Because if you notice in here, compared with a random 50%, we are sampling much less voxels. So with this one, we increase a little bit the sampling density, and we use optimization algorithms to try to recover the information. And this was some simulation results. On the left side of each stack of images, you can see the 4 measurements, one for each camera. On the middle, you can see the ground truth video, and on the right side, you can see the reconstruction. And you can notice that even it's a bit noisy. I really like, for example, the reconstruction of the trucks in the highway. You can see in the measurements the distortions related with rolling chatter. But the good thing here is in the reconstruction, in the parts you can see the trucks, there is no rolling chatter distortion. So with this, we are solving 2 problems at the same time. And of course, then we tried in experimental setup. We use some analog oscilloscope to see if we can measure the beam traveling across the screen. And also we can reconstruct the motion. So on the top we have a sinusoidal signal, and on the bottom we have a triangular signal. And still, we are tackling so much, the density is so low that we still going to have noise, but we can notice the dynamic movements of the beam. So the conclusions of this work was that we use CMOS as an extractor of temporal information. Even it's not so good, it was good in the sense that we get temporal information from nothing, basically. And using an array can effectively increase the sampling density. Well, increasing exposure also increase multiplexing, so we can do a trade-off between the design parameters. Then we have the next work, which is called shuffled rolling shutter for snapshot temporal imaging. The concept was the same, using rolling shutter as our coded aperture temporal imaging system. But the problem arises in the first work was we didn't have too much control. We only have one row each time to reconstruct. And this is not a good design for sampling. So then what happens if we can re-scramble the circuit? I mean, the first row now is a distribution across all the sensors. So here you have the theoretical circuit. Suppose that we can change the connection of each pixel. Now we scramble all the pixels across the sensor. And the shutter functions should be like this. So then we explored two ideas. First, as traditionally in compressed sensing that use random samples, we shuffle the pixels also in a random manner. But we noticed that this is not so good, because if you notice if you choose any color you see, you can notice that there is some parts where it's more dense and other parts where the colors there are not much present. So we already noticed that maybe we can design this and improve the sampling across the sensor. And then we came with this optimized shuffling rolling shutter. The optimization is based on a problem in mathematics, which is called the sphere packing. So if you have a limited amount of spheres, what is the best way to fit all the balls in a box? So now in this context, each sphere is representing one voxel and what time. And then obviously in mathematics, the sphere packing problem is a continuous problem. So here we have to adapt it to a discrete, because pixels cannot live in interpixels. So you have a discrete spaces where the pixel can live. And we have this random approach after the balls are not well packed. And if we calculate the distance between each ball, you can notice that some balls are closer than others. So this is going to lead to uniform sampling. Then we optimize, and you can see the balls are much better packed, and the distance is the same for all. So with this, we can guarantee a uniform sampling across the video. And to reconstruct, now that deep learning was becoming really popular back then for this kind of task, we also proposed to train our own network to reconstruct the video. So this network is basically a unit, but rather to use 2D convolutions, we use 3D convolutions. The idea of that was because kernels exploit correlation in unit, but if the kernel is 2D, then the correlations to be learned is going to be only 2D. By changing this to 3D, now we are exploiting spatiotemporal correlations in the features of the video. And this is our simulation results. So we compared this method with interpolation, and also we compared it with tensor completion. You can see the three types of measurements in each row. First is traditional rolling shutter. This is a snapshot only using one camera. The second one is the random approach, and the third one is the designed approach. So you can see that rolling shutter cannot reconstruct nothing in the temporal side with only one shot. But in random or designed, we have the exact same amount of information. So we only change it when we are measuring it. And you can notice that even with interpolation, we have a really good results. But obviously, using deep learning, we can approach more to ground truth. And this is good for any kind of motion. So you can see that we can have different kind of motions and all reconstruct really well with the same snapshot. I really like the one in the middle, which is this woman running, because here we have two types of motion: local, which is the person running, but also you have global movement because the camera is moving, and you can reconstruct really well in that case. And to test this idea, we also use our implementation, which is the same as cacti. We only change the sampling matrix we are sending to the DMD. And this is our experimental results. So first, in the first row, you have the measurement. This is a continuous acquisition. In the middle one, we have our reconstruction. And the third column is a reference, high-speed camera. And you can see we can achieve almost the same information with only 3 captures in this full sequence. And we lose a bit of spatial resolution, but we think that is okay. Because these cameras is just integrating at 15 frames per second, and we can mimic 500 frame rate per second camera. So we are saving a lot of space in memory and it's much more efficient. And that was the conclusions we took from that study. So by modifying the CMOS sensor, we can allow a snapshot compressive temporal imaging just with a simple modification. And shuffling the pixels get a lot of results. I mean, and the improvement between traditional and shuffled rolling shutter is quite noticeable. And then we have our third work. And this one is compressed video via illumination in infrared. So this idea was basically based on this work proposed by Raskar in 2006, which is called a flutter shutter. But when they developed this camera, they use it for PSF deblurring. So the idea is not to reconstruct video from this concept. And this is how it works. So basically we have an object which is moving, and we randomly open and closing the shutter of the camera. So this is how the tensor of sampling should behave. So now we have a full exposure of the sensor, but this is changing in time, the activation. And then later on, some workers try to reconstruct video from this, because this is also a compressive scheme. But you can notice that the results are not quite good, because it's obvious the mask design of this also is a really bad conditioning to reconstruct a video from a snapshot. So I tried to see if I can improve this, but I was sure that doing the same thing is not going to improve. So I proposed to use a multi-shot system. So here we changed, rather to open and closing the shutter, we are using active illumination, and we are going to store 3 measurements. So one of the start, the middle one is going to be code with random opening and closing, and the last one is going to be one to interpolate. So I designed this system as an interpolator, as a guided interpolator with the coded measurement. And you can see that the motions, the measurement or the acquisition is exactly the same. We share the same forward model as flutter shutter. And I implement this system using infrared illumination just to not bother the person, because we are going to have strobe effects of turning out high power LEDs. And we design our quantization system, which is going to be the timing in green. Then we have our illumination signal, which is going to be a random in this behavior, and our camera. So first, if you notice in the camera, exposure of all the coded frames. And to have our third measurement, we just recycle the first one of the previous cycle. And also to compare us with state-of-the-art frame interpolations, we use another camera as a reference, which is going to take the same amount of measurements, just it's going to be a short pulse on each tube. And to reconstruct, we also use deep learning. We train this network, which is a cascade of units. In this case, the cascade of units are 2D because we want to use it as an initialization. And then we propose to reconstruct the video, use a spatiotemporal transformer, which was becoming really popular for computational imaging tasks back then. And this is our simulation results. So in the first two rows of each stack, there are two state-of-the-art frame interpolation methods, and our third one is our approach. And wait a second, I'm going to drink some water. So here you can see that for complex motions, frame interpolation cannot reconstruct. So one of them I like is this snow ski. You can notice that frame interpolations, oh, sorry, I want to correct. The first column is ground truth. The middle one is frame interpolation. And you can notice that our approach behaves more similar than ground truth because frame interpolation cannot infer so much motion. They tend to just infer linear motions. So when you have acceleration or change on direction, you have these weird motions, for example, in the dancer or in this carousel. And experimentally also we tested, we drop a camera cap down to a ramp, and now we test two frame interpolations. So this is a continuous acquisition. On the top row you can see the measurements. They are stacked in color, so the motion you're going to see as a difference of color. And you can notice that the motion of our approach is more smoother. The cap disappears and reappears in frame interpolated cases. But even, this is still a difficult task, so there is still some noise in the motion, even, especially when the motion is become more larger. But it's capable to follow the trajectory of the cap. So the system here proved the capability. By adding extra measurements, you can also use it as a compressive measurement, as a compressive system. But as you can see, there is a limitation on the speed of the motions. If it's too large, then the frame interpolated or our approach is going to be difficult to reconstruct. And we implement the system in illumination, but this is perfectly doable with a traditional flutter shutter. And then this is the final work of this presentation. So here I developed a scalable coding strategy. And first, I want to talk about, again, of traditional cacti. So as you know, we cannot multiplex forever. And we use random activations of the sampling. So this is good for multiplexing measurements. Compressive measurements are good also to signal to noise ratio. But they have this scalability problem because if you have even a deep neuronal network reconstructor for this, also the neuronal network has to scale up with the measurement size. So if you want to reconstruct 4K or 8K video, we need a deep learning deep learning network to handle this in video memory, which is difficult. On the other hand, other words, I propose to use subsampling. Just the difference between subsampling and compressing is that here we are not stacking time in the same pixel. So each pixel is separated in time. So for example, the first frame is yellow, and the third and fourth are cyan and blue, and the last one is green. But then in the measurement, we know exactly what time is each pixel. While in the compressive measurement, we first have to disambiguate the problem. And there are some words that do that, but the problem of this is signal to noise. So we are measuring less information, and we also lose some spatial resolution because we have to do decimation to reconstruct. So then I propose this system. So basically it's combining these two concepts. We use the concept of subsampling to disambiguate the problem in small stacks, but also each of these stacks are made of compressive measurements. So the advantage of this is that we can solve each problem individually and then stack it to reconstruct the full video. And this is an example of how the coded aperture should behave in this system. As you can notice with previous approaches is that the sampling is more sparse. And you can notice how it's filling up each subpixel region. So then we collect this data, we have our measurement, and our first step is to separate each temporal stack. So now we can call this sub-problems. And because these sub-problems are smaller, we can use any standard optimization to reconstruct or even pre-train neuronal networks. We don't need to train our own network in this case. So we solved this sub-problem, and now we are having a small version of the video, also in space and time. So then the next step is to going back to the original full resolution. And we know the positions in space and time of each of these sub-problems, but now we give up information on subsampling, so we have to try to recover this. And to recover this, you can notice that going to the original resolution, we have a lot of information to fill. And then we can use standard super resolution algorithms, or we can use implicit neuronal representations to fill this information. And this is an example of this is simulation, but with the picture of the left. Oh, sorry. Oh, this should be a video, but it's not playing. So let me show you the experimental results. So these are made of 3 measurements, and on the right side is the reconstruction. Oh, it's also not playing. Oh, sorry. You have to believe me that this is a really good result. So then we propose a straightforward and powerful approach to reconstruct arbitrary size of high-speed video and high resolution. The main challenge is to fill the missing information because we lost a lot of information during subsampling. And also using deep learning can be an effective way to fill the information because we can manage it in a small package, not requiring too much GPU memory. And with this, I finished the works. So the main conclusion of this thesis is that there is a lot of, in the current technology, there is a lot of ways we can exploit the disadvantages of sensors, of using a really good signal processing techniques to improve the reconstruction or sample really high dimensional data and avoid using so much complicated optical hardware. The concept that make all of this possible is the video sparsity. So as we know, if we exploit correlation between the natural signals, we can measure a lot less than we need. So we can be more efficient on how we design the sensors of the future. And also neuronal-based reconstruction are here to stay. So they're going to become better and better. So we we have to be open to accept these new techniques. If we know what they are doing, I think we can be a great help to the computational imaging community. Some future improvements of all of these works can be the most obvious one, that is color. I mean, a good video also has a good color. So we can also incorporate, for example, Bayer filters, or we can go further and add in multispectral videos. Other next approach can be redesign the CMOS readout chips. So if we incorporate this CMOS sensor with pixel-wise integration, all of these techniques will be more ubiquitous to, for example, cell phones, and incorporate the idea of compressed sensing directly on hardware. And also we can start using this system in real-world applications. So deep learning allows us to real-time reconstruction, for example, and we can start using this in many fields. So this is a brief summary of all my works during the PhD. So I give 4 conferences, and 2 of them are related with this thesis. And also I'm very proud that one of the shuffle, roll, and shutter concept was published as a chapter in a book edited by Professor Jinjan Liang. And I published during my PhD 4 papers, and 3 are related to this thesis, and the middle one was, I also am proud that was selected as editor pick. That was my first time, so I'm happy. And also this year I was invited as a speaker to present in the Optical Imaging Congress, and presenting this same thesis dissertation. So with this, I finish my presentation, and thanks for your attention.
Thank you, Felipe. Thank you, Felipe, for your presentation. Now we start with the question of the commission. We start with Dr. Horisaki. Should I use the microphone? I don't know. I think it's fine. Yeah, it's not. Yeah, that's good.
Thank you for your presentation. First of all, I really appreciate your contribution to computational video imaging, and I believe it is very important, and I appreciate it. And I have several questions, a little bit key, but please excuse me. Okay, and okay, so could you go to the page 29?
One second.
No, this one. Go down. Maybe go up. Go up. All right. No, go down. Right. So, so basically, I guess you worked on. So in your thesis, basically, you suppose short exposure time.
Yes.
But as you mentioned, there is an option of long exposure time.
Yes.
So could you explain a little bit more about such kind of approach and your method?
Yes. I mean, there is a trade-off between shortened exposure and long exposure. So for short exposure, we assume that the exposure time is the same as the readout time. So now each time one voxel is sampled. So this is more kind of a subsampling approach. So I didn't mention it, but we use a little bit more of multiplexing. So for these results, I use a long exposure time, about 3 times the readout time. So it's kind of like this, kind of like the middle one, just to sample a bit more of space, and also don't have reduce the number of frames that I want to reconstruct.
Okay, so could you go to page 33?
30, this one?
Yeah. Could you start the movie?
Yes.
So I can see some artifact on the pulse which go to the opposite direction.
Yes.
So what is the reason?
I think the reason back then was this system was not perfect. There was some crosstalk between temporal channels, and probably the scene I chose it wasn't the best because I test natural scenes with more bigger objects, and this one which is a sparse point moving in space. So probably this wasn't the best situation for the system to test.
So let me double check. So this is not caused by sort of experimental error. It is caused by theoretical limit.
No, you're right. There is also some experimental error because I have to calibrate the region of interest of where each camera was pointing out, and there is also some distortion of the lenses that become this hard to calibrate perfectly.
And could you go to page 37? Yeah. So as you mentioned in the conclusion part, how difficult to fabricate or product make mass product of this kind of random pixels?
Yes, that was a hard question to tackle back then too. But the idea that we are not a sensor manufacturer, so I was not focused too much in the circuit itself, but rather on the theoretical part. But also there is some available sensors on the market that use pixel-wise exposure. So this, I think this one is much easier because this doesn't need to be pixel-wise. It can be just row-wise and just bypassing the connections.
Could you go to the page of sphere package?
Yes.
Okay, so my question is, can you feedback this concept for the previous case, like camera array with rolling shutter? So when you suppose camera array with rolling shutter, there are some empty space.
Right.
So can you feel the empty space like this kind of concept?
You mean with the traditional rolling shutter, right?
Yes, yes.
I don't think that is possible because rolling shutter is really restricted in what you can do. I try to move, for example, put 8 cameras rather than 4, and the region of interest, the camera is a bit down. So now the first row is like in the middle of the next one. But there is a limitation of you can do so. Adding more cameras is really not much improving the concept. And in the paper, I present that. I present several results by adding 1 camera at a time, and there is a plateau. That adding more, there is no more improvement.
And in the next project, so you chose modulation by illumination.
Right.
And as you mentioned in the conclusion, in the chapter, so you can also choose, what should I say, coded shutter.
Right.
So why did you choose illumination rather than?
Well, to be honest, the real reason for changing the implementation wasn't so scientific. When I was in the internship on University of Arizona, Professor Brady already has a project to use active illumination to measure the speed of baseballs. So I start with that project, and then when we did the pulse illumination, we can see if we can do this further and use arbitrary video.
And in the last topic, I like the concept because you can take a balance between spatial resolution and also compression ratio.
Right.
But I guess there is also a trade-off between them. So could you give some comments on that?
Yes, I mean the trade-off. I think the worst trade-off is the same as the subsampling approach. That is, you lose spatial resolution, and was one of the most difficult tasks to challenge. I think when I get results with implicit neuronal representation, I get really good results because implicit neural representation manage the positions and the correlations of all the video and all the space in a really efficient manner. And then I think the other challenge is the size. I mean, now the size, the amount of subsampling can do is dependent on the sensor size. So I think this restricts a little bit the design parameters of the coded aperture.
So, and my final question is about your contributions to each project.
Mm-hmm.
So, how large, for example, how large is your conceptual contributions on each topic?
And the first topic, Professor Esteban told me you can use rolling shutter, and then I start developing that concept. On the second, it was Professor Esteban's idea. I just make it work. And third and fourth one are completely my idea. Oh, and sorry, and in the shuffled rolling shutter, Nelson Diaz, the postdoc of our lab, developed the idea of using sphere packing to optimize the sampling. I just developed the network and also tried the implementation of the random approach.
Okay. Thank you for answering my questions. That's all.
Thank you, Dr. Horizaki. And the next question is for Dr. Pablo Mesa.
Should I speak with the?
Yeah.
I don't know. Can you hear me from here?
No,
or-
it's fine.
It's fine.
Yeah.
Okay.
Better.
Well, before anything, congratulations, Felipe, for your presentation.
Thanks.
It's kind of difficult for us to evaluate your thesis because you have a lot of production. So that's really good for you and for us because we end up reviewing something that has been published before. So it's good material. It's easy to read. So
Thanks.
before anything, the thesis was really good in terms of the writing. Okay. I separated my question in terms of the chapters. So first of all, the rolling shutter scheme. You can see that despite of using that technology, and at the end, what you are designing is a measurement scheme in terms
Right.
of the sensing matrix that you are developing.
Right.
So instead of using a random measurement, you're using like a correlated measurement in terms of like from the upside down to the left to the right, right?
Right.
So did you calculate the conditional number of the matrix to see how it was performing?
Back then, no, I didn't, but I suppose that was really bad.
Yeah. So because as you said, it has some limitation in terms of the scalability. If you increase the number of cameras, you reduce, as you say, the region of interest
Mm-hmm.
because you are not able to like sample the same part of the scene,
Right.
so you cannot correlate the measurement. So
Right.
you have any idea of how to solve that in the future? Do you have any device, any element that you have managed?
Yes, I mean for when I did experimental, I used calibration points, but I think you can exploit, for example, feature extraction algorithms like SURF to match the positions of each field of view. But probably there is going to be limitations that way because we need almost sub-pixel precision to get that. So also you can complicate the optical complexity, ironically, by sharing the same lens.
Yeah. You can use as an easy way is to just split the incoming light into
Right.
using just a beam splitter instead of one to see the scene and then you avoid the problem of the region of interest. Right.
Right,
Okay.
right.
Okay. So I will comment this on the end, but I mean you can see the connection between the chapter 2, chapter 3, and the chapter 5 in terms of how you are developing the technology. Because
Right.
in the chapter 2, the shuffle rolling shutter,
Mm-hmm.
you are like moving aside from rolling shutter and mixing up the electronic readout scheme.
Right.
So you're using there the sphere packing approach, but as same as rolling shutter, you're not doing like multiplexing the temporal domain.
Right.
You are just measuring different point space for a temporal mark, right?
Yes, you're correct.
Okay. So I had a similar question that Professor Riochin instead of the implementation, because in the lab you can like test that with the DMD, but as an electronic element, the that type of readout camera, it is able to purchase on the market, but it's not like cheap or easy to use.
Yes, I mean, back in the conference when we present this idea to experts on sensor technology, they say this is feasible to make, but obviously, as any new technology is going to be expensive at first, and also I think this concept can work well with cameras, because if you don't going to take video and just a photo, the artifacts disappear or related to shuffling.
Yeah.
And you can have a perfectly normal working photographic camera. And then if you want to have, for example, high-speed mode, then they can activate this system to exploit the rolling shutter.
Yeah, but because at the end you are eliminating the necessity of the coded aperture element and moving that work to the electronic stage.
Right.
Yeah, but similar problem you can find if you are using the DMD is that how many frames can you divide if you are not multiplexing? How many frames can you divide the segment of the sensor? Because if you are coding more frames, you are limited the amount of light that each frame is measuring.
Right. Right.
At the end, you can adapt, like, you have all the light captured by each sensor, but if you are having like 100 frames, you will have only a few pixels measurement that time. So
Yes, but in the good thing about this is that in high speed applications, you are expecting that you are going to have a low light throughput.
Yeah.
So that's why you have to buy illuminators for high speed.
High power laser.
Yes.
Yeah.
So
That is a traditional problem for
Right.
imaging.
Right.
Okay. The active illumination scheme. I think that is the fourth chapter. Can you explain it to me? Because I didn't understand. Are you activating each pulse of light in different time? So you have this one, the left one, the right one, in different time. That is what you're doing?
Yes. So rather to use
Because I don't remember seeing the experimental setup on the document.
if I didn't put it, probably I was mistaken, but yes, this is the experimental demonstration. So on the top you can see 6 LED, high power LEDs, and we synchronize the acquisition of the camera with the LEDs. So each time, in the short exposure time, if you can notice, the timing signal is coinciding with a pulse of illumination.
Yeah, but you are activating each one separately or at the same time?
We try a lot of things. So for closed environments, we can use only one, and we try to activate different so that work I couldn't finish in time, but it was really interesting because The funny thing of the LEDs, it has, when you focus, you can form kind of an image of the LED projected on the object, and we want to use that as a pattern for illumination. But we couldn't finish that, so the results that I have, it was with 6 illuminators activated at the same time.
Oh, okay. So there's six are activated at the same time. So you can replace that with a bigger
Right.
light. Okay.
Right.
Okay. I didn't understand what you use 6.
Oh, well, sorry for...
Okay. You understand the limitation in terms of using active illumination? In terms of passive?
Yes. There is a lot. I mean, crosstalk, if more people have the same system, you cannot notice if it's lambing coming from your system or the other system. And for also in this implementation, the light throughput was a really good limitation because we use filtering and we have to have enough throughput to the sensor for far distances. And obviously the most obvious one is daylight conditions.
Yeah. So it will require a lot of calibration if you are going to take that to the outside.
Yes, we tried to take measurements outside, but it was in night just to have a good signals. But yeah, in daylight, Professor Brady was, it wasn't worried about that, so.
Yeah, but he has money, so he can solve that. Okay, so in the next chapter, give me a second. In the next chapter, you propose, now you are multiplexing.
Yes.
Yeah? Despite you are doing subsampling, now I can, again, you can see the relation between chapter 2, chapter 3, and chapter 5 in terms of how you increase the complexity of the problem.
Yes.
So this is a good relation because you take it to a trip in terms of how you develop it each stage and how you increase the efficiency. So that is good to see. So I can see that, and you talk this with Professor Bisaki, is that you are compromising spatial resolution.
Right.
So you are starting to see that more information, you will need a little help in order to disaggregate the information, right?
Right.
So if you mix up with this with the spectral domain, like taking red, blue, green, or more band, you will have to sacrifice more information, more in terms of the resolution, right? Because here are just monochromatic image. You have spatial and temporal information. Right. So you are taking like less resolution in terms of spatial resolution to improve the temporal resolution. But if you add that like polarization or in the spectral domain, what would you will sacrifice? I mean, what do you prefer to?
Yes, I mean that is a good question, and I agree with you. There is a huge problem with this system related to that. But when we submit this paper recently, so the idea we have on this paper is the end user will have the shoes. So we propose this design as a parameter. It's parameterized. So depending on what you are willing to sacrifice is going to give you the best mask design for that purpose. Yeah. But yeah, I mean, we cannot invent data. So we are sacrificing data. There is no way to recover it.
Yeah. Also, I don't remember the parameter. I believe that is K for each subsampling.
Oh, sorry. K is the quantization of the frame, basically.
Okay. So like there you have 4 subsamples, right?
Right.
So but you just said on your thesis you try different values of K, right?
Right.
Okay, so is that parameter related with the type of scenes that you're working? I mean, because at the high number, you will sacrifice more spatial resolution?
I think I didn't present it as a choice for a specific kind of a scene, but I think I can say the usefulness of that. For example, if you know you are measuring large objects, but you want to measure across an entire day, you can sacrifice more of a spatial time to, spatial,
resolution.
and get more temporal multiplexing.
Yeah. So if your scene is not like rich in terms of spatial information, you can sacrifice that
Right.
one, so
Right.
improve the other. Okay. And the last question is more like general. Did you notice that your thesis is named Coded Aperture Strategies,
Yes.
but you use that in the second, third, and fifth chapter, but in active illumination that you are not using Coded Aperture?
Yes. I noticed
It's not bad, but you noted that, right?
Yes. But I'm disagree with that. I mean, we can say that we are we are codifying the aperture of the illuminator.
That is a stretch, but okay. That is enough. Thank you, Felipe.
Thanks.
Thank you, Professor Mesa, for your question. Now it's the turn of Dr. Hermosilla.
Okay, thank you, Felipe, for your presentation.
Thanks.
Very good for me, and in addition, congratulations for all your work, and for our school. We are very happy we have some students like you, and I have some generic question for your work. I have some doubt, and after I want some more philosophical question.
Please destroy my neuronal network.
Yeah, you know. So in the 40, the slide number 40, you use here a unit neural network. So
This one, right?
yeah. Here you comment that you use a 3D unit, and here this is the reconstruction for snapshot, right?
Right.
Yeah. So you can use here temporal or time step for the unit.
No, in this case, we have to pre-process the measurement.
Uh-huh.
So basically, this module on the left, you can see we have the matrix measurement.
Uh-huh.
We multiply it, but basically we remap the measurement, and we multiply it by the shutter, and that tensor enter as an initialization video for.
Yeah. Okay. Two questions here. Why you use this unit for what for is your why you choose this neural network, and after the reconstruction is done, the physical property of the scene is maintaining, or you can obtain, for example, in your when you use the sinusoidal scene,
Right.
the physical is not represented in the reality, because the sinusoidal is for two not in one direction, for example.
Okay, I will answer the first question. The second one, then we can clarify.
Okay.
But I choose unit because it's a standard architecture to do compressive reconstruction. So basically, as you enter the tensor, the idea is that the encoder is going to learn the implicit features of the video, and then map these features to complete the rest.
Mhm.
And it's a really standard architecture for computational imaging. And the second question probably is related to 3D motion.
Uh-huh.
You mean that?
Yeah.
Yes, I mean, we didn't test 3D motion, but if you notice in the reconstruction results, there is motion that is going further away the camera and closer. For example, in this bottom one, these are coffee beans in a blender, and they go all directions.
Yeah. Okay.
And this is ground truth video, so we are making sure that not inventing
And-
some
yeah,
motions.
And related with that, what the training data? Which training data you use to train the unit here?
We use a open source video dataset, and we use the standard approach, splitting, validation, testing, and training, and data augmentation was needed too for,
Okay.
we use rotations
Okay.
and reflections.
Okay. And in the blurry case, for example, in the slide 52, now you use temporality, right?
52, right?
Yeah.
Yes.
Here. Yeah. Here you can use now time step, right?
No, neither. No. That's why scalability is a huge problem for this method, because you have to put all the video at once.
Ah, okay.
And if you notice, there is a difference. So you can say that this network is just a unit, in the MB, and we are missing the pre-process stage. So back then I was trying the same pre-process approach, and it didn't work. So I proposed this module to act as a preprocessor for the video.
Okay. And with the unit, you don't use, for example, operation in the latence. For example, between the encoder and decoder, you can operate in the neural network. So you use only compression and decodification?
Yes, because in my experience, now because back then I didn't know much.
Okay.
Manipulating the latent space, you don't have too much control of the output. You can get like weird motions that not related with the measurements. So in the context of computational imaging, you want to reconstruct the information you are sure you measure.
Okay. So okay, and another question was more philosophical or more to understand. In the 22, you choose you show your mathematical equation in the 22. So you can use directly a convolutional neural network to represent that. Because the representation is very similar, and you can use different feature maps. So can you explain about that?
You mean this one, right?
Yeah.
So
you can modulate using the CNN?
Yes. There are some works that directly embed the shutter. So it's acting not only as a reconstructor, but a shutter designer as a neural network. And there is a lot of research going in that direction. So I probably in my future is going to have a lot of works related to that.
Okay. So the last question is, you showed in the very beginning of your presentation the SORA video,
right,
for diffusion transformers. So what do you think about the use reconstruction and generative model in together? So what do you think about this idea? So when you reconstruct it and generate between or something like that. So tell me about that.
Probably the answer is really similar on the other question, that the computational imaging community is try to avoid generative models, because you want to make sure that you reconstructed what you measured. And using this kind of technology probably is not going to be very popular in the near future. That is just my opinion. So for example, if may Horisaki-sensei explain if the Japanese words you see in the video make sense? Yes? Oh, that's good. So that's really is becoming really good.
Yeah, you visit, right?
That is Shibuya.
Sort of.
So, okay, thank you.
Thanks.
Thank you, Dr. Musilla. I don't know if Dr. Isaki or Dr. Mesa have more questions. No more questions? Then, Dr. Vera, do you want to say some words about the Felipe's work?
Of course, and before that, maybe you can put the video we are expecting.
Okay.
Thank you, Mauricio. Thank you, the rest of the committee, for showing up. So first of all, I have to thank Felipe for his hard work during these years. And as I mentioned them, when they start working, it's really a trust relationship. I mean, nobody knew me, and these guys show up and say, oh, you want to work with me? Why? And so I'm glad he trusts on what we wanted to do, and he really is really embedded into the problems, and he's already, you know, the originator of the solutions, you know. So there's a progression from when you start, you tell them what to do, but suddenly in just a few years, he's telling me what to do. And that's what we really expect out of a PhD student, that he become completely independent. And that's what Felipe came. So the other thing I should mention is that also Felipe is only showing a portion of his contributions. He made contributions to our group, to other fields. So we expanded some ideas to spectral imaging, and that was successfully published. And he also came with a completely idea of his own to one of our adaptive optics problems. So, and that was nicely published. So, and that by itself could have been a PhD thesis. So I'm really glad of his work. And this is interesting because this is completely, we just came up with this idea. We have a problem. We need to compress more. We need to make more efficient usage of sensors. We don't, especially if we want to have it remotely. And he came up with these ideas of, okay, let's do it. So this is only 3 frames, and we are reconstructing, you know, 1,500 frames. So maybe you can do the other one.
Which one?
In All Sky.
Oh, okay. Let me find it.
So I'm fully happy. I'm glad with Felipe results. So I also believe in that. I mean, he's a great, you know, team player. He's always looking to train the other guys, so that's very important to us. He's also lots of teaching experience, which is nice. So I think he will be a great asset to any group in the world, and hopefully he can keep with his academic endeavors. So
this is one capture.
So this is very cool. This is only one picture on the left, which, I mean, you cannot see like nothing. I mean, it's a coded picture. And he's basically disentangling, I don't know, 500 frames?
500.
So I think it's just fantastic. Sure. Pixel count?
2K by 2K.
So yeah, I don't have way more words to say how glad I am by this situation. So I would be just sad if Felipe has to leave the lab. So anyway, gracias, Felipe.
Okay,
Thanks.
Dr. Vera, thank you. Thank you very much for your words. And now the Commission must deliberate the qualification of Felipe. For the reason, I invite all of you to go outside of the room, and more later we.
Thank you.
Ay, ¿dónde está? ¿El otro?
Esta es la adicional.
Aquí, yo creo, ¿no?
Ahí se escucha. La comisión se reunió, como ustedes ya saben. Ya, cada uno dio su opinión sobre el trabajo y la respuesta a las preguntas que dio Felipe. Y voy a leer ahora la continuación del acta. ¿Ya? Considerando la exposición del tema realizado por el alumno y sus respuestas a las preguntas realizadas, cada integrante de la comisión calificó el examen en forma individual y secreta, promediando las evaluaciones, siendo esta la nota de 7,0. En consecuencia, y considerando el reglamento del programa de doctorado actualmente vigente en la escuela, el promedio de notas de sus estudios y lo obtenida en este examen, la dirección de la escuela enviará al señor decano el expediente de grado en los siguientes términos. La Escuela de Ingeniería Eléctrica de la Facultad de Ingeniería de la Pontificia Universidad Católica de Valparaíso solicita al señor rector de la universidad se otorgue a Felipe Orlando Guzmán Vega el grado de doctor en Ingeniería Eléctrica, con la calificación final de 6,7, que corresponde a una nota conceptual de summa cum laude. Muchas felicitaciones, Felipe, y a la familia.
Doctor Vega. Felicidades.
Están todos estamos muy orgullosos.
Muchas gracias.
Todos tus logros. Sean muchos más.
Muchas gracias.
Doctor Felipe, felicitaciones. Muy buena persona.
Muchas gracias.
Eso, de instrucción, ¿no?
Primero está. Gracias. Ahí va. 1, 2, 3. Otra. 1, 2, 3. La última. 1, 2, 3.
Eso, un bonito recuerdo. ¿Está con perfume?
Sí.